All right, everybody. This is one of our geometry lessons. This is the 6.4 proportionality theorems lesson. And this is a new approach that we're going to take, me and Mr. Cruz. In case you don't know who I am, this is me, Mr. Lau. And so we're going to see how effective some videos are going to be for you guys if we find that, or if you find yourself needing some of that extra help or re-seeing a problem and whatnot. Okay. And so what you should see on the board now is 6.4 proportionality theorems. It's pulled up on the reading theme board for me so that I can go ahead and work on it with you guys and whatnot. So the first thing that we are going to do is establish that, well, while Mr. Cruz and I aren't exactly working on the same thing at the same time, we're still working pretty similarly. So we're going to do the best that we can to illustrate that we have the exact same examples and the same theorems and whatnot. So if it's a little different from how I teach it, from how he teaches it, that's perfectly fine. And in all honesty, maybe you'll find that we teach a little differently and you prefer one or the other, and that's perfectly fine. Okay. And so for the first theorem here, 8.6, something that I made sure that my classes knew is that whenever we see this 8.6 and this 8.7 here, is that we're jumping around a little bit in the textbook that we're using here. And so the person who made the notes kind of took pages out and theorems out from one section and put it into our Unit 6 material and whatnot. So try not to get confused with 6 and 8 and whatnot. I know it's a little tricky, but I think we'll be all okay. Okay, so with this first theorem here, the triangle proportionality theorem, something that I really say is the most important is going to be this if-then statement. Okay, if you can understand the if and then part of the actual theorem itself, more likely than not, you don't need to read the paragraph. However, the paragraph is there for you to reference to if you need to. And so if we look at this, it says if segment TU is parallel to segment QS, which are these two blue ones right here, then RT and TQ, or RT over TQ equals RU over US. Now, something I want us to really pay attention to is that if we look at this first proportion here, it is not like how we've seen it beforehand with other triangles, where we actually see we take RT, which is the segment I just marked now, and then we also have TQ all in one proportion. Now you may be asking yourself, why are we doing that? And that's a great question, okay? And the answer is a little bit more complex than just saying we have to. But for any triangle that we have parallel lines inside of it, basically a triangle inside of a triangle, then we have to use these theorems in order to show that they are proportional to each other. Okay, and so that's how we're going to approach this lesson. But definitely these are the two most important things, is that for sure we have not only RT and TQ, but we have RU and SU as well. Okay, and that's going to be notated with this purple. Okay, so if you can understand that this is what we're doing, this is how we're going to approach the problem, and we need to use the same side for proportions, you should be perfectly fine with this theorem. And in fact, I would even add in on the side proportional sides. Okay, you're putting one segment on top of another segment, part of the exact whole segment. So in essence, you're taking segment 1 and putting segment 2 on the bottom, if you want to think about it like that. Okay, I would just go with the approach of whoever teacher you have and how they explained it. But however way you understand it is going to be better for you. Also, by the way, for students who are not my students, I do have poor handwriting at times. So if you ever have any questions about what I had written on the board, you can come over to my class and ask me and kind of figure out what I was trying to say here. Okay. Then we have the converse of the triangle proportionality theorem. Just like any other theorem, you could technically switch around, and that's what the converse means. We switch around the if and the then statement. You'll realize that from the previous problem here, the then is now the if and whatnot. And so for this theorem, this one's mostly going to be used to prove parallel. By technicality, you can also prove some proportionality and some similarity and whatnot. But for the most part, I like to think about it just proving parallel. And something I did with my students as well is that what I did is I drew two pictures like so. You don't have to be any artist of any kind. You can just draw pictures like this, and that's perfectly fine. And so what I would add on to this, you take the first triangle on the left, draw another line, make it about as parallel as you possibly can with this segment on the left. And you're going to draw those two triangles that indicate that these are parallel to each other. And so what I would write here is sides proportional. Okay. And since we know that the sides are proportional, we can also say similarity. However, on the opposite side, we're going to try to make a line that's very much distinctly not parallel. So for example, like this kind of line. That is for sure not parallel with the leftmost segment. And so what we would say here is sides not, oops, I'm running out of space there, not proportional. And by proxy, we would say not similar as well. Just like so. And as I'm looking at the time now, it took about 8 minutes for that intro, but some of it needed to be said. And I like to kind of really explain things as well as I can in these soon-to-be videos and whatnot, so that we get the most amount of understanding per video. But again, if you have any questions, though, feel free to reach out to me or Mr. Cruz at any point that's appropriate for those questions. Okay. But we are going to move on. We did not do a turn and talk, at least for my group. So we're just going to go ahead and move on to that first example. And the way I approach this problem, obviously you want to read the problem first, right? But I want to start even before that. Like, what are we actually trying to do here, right? We're working with similarity. In similarity, we use the idea of new and old. So the first thing I'm going to do is establish what is my old and what is my new. The second thing I'm going to do, I'm going to find my proportion. And the third thing I'm going to do is I'm going to solve. Okay, solve is a little ambiguous. You don't really know what you could be doing or could be trying to do. So we'll just leave solve to be up in the air for us. Okay, and so now that we're ready here, let's actually read the problem. So in the diagram, we're shown that QS is parallel to UT. Now, immediately, we should be kind of triggered to think, well, I know that two of these segments are parallel. And if I look at the diagram, it shows that's the case. And that we should be thinking about that first theorem we just looked at. And so if we look back to that theorem, it said if we have two parallel lines inside of a triangle, that must mean that the sides are proportional. So we're going to write proportional sides here. We'll keep moving on. RS, ST, and QU all have those values, which conveniently have already been laid out for us. and we want to know what the length of RQ is. Okay, so we look at RQ or QR, either way you want to say it. We look at it and we say we don't have any variable, we don't have a number for it, and we're trying to find the length. Well, what we're going to do is we're going to give it a variable. In this case, we'll give it an x. And you'll see in the next example what we do for the variable. But for now, we'll just keep it as an x. And now we've set up the problem exactly how we want it to be set up. And so we're going to follow the 3 steps that we have here. Now, for my class, and I think Mr. Cruz's class as well, we've always established that the leftmost, I guess, introduced figure is the old, and the rightmost is the new. But what I want us to kind of understand is that it doesn't really matter which way you're doing it, so long as you are consistent. Okay, so for instance, what we would do normally, I guess you can say, would be QS would be old, and UT would be new. But realize if we chose QS to be new and UT to be old, that will work the exact same way as well. Okay. But for this example's sake, we are going to use old and new in this way. So I'm going to label old for QS and new for UT. And what I'm also going to do is that I think a lot of us get mixed up on which values belong to old and which values belong to new. And so here's my fix for that. I'm going to take this highlighter. I'm going to shade in everything that is old. Oh, yep. Sorry about that. Don't know what that was about. I'm going to highlight everything that's old. Then I'm going to highlight everything that's new. Just like so. Okay, and what this helps me do is it helps me recognize exactly which values belong to which old or new. So in this case, now that I've seen this, I can say that my new values is going to be U and Q, and for segment UQ and segment ST. Whereas my old values are going to be QR, segment QR, and segment RS. Okay, doing this is going to be able to help you understand which one you're actually supposed to be working with. Okay, but now we've established our new and our old. Good check mark there. Now we just have to find a proportion. And in order to find a proportion, we're going to take the approach what it says in the theorem. The theorem said that if we take QS and UT, and if they are parallel, then we're going to take, in this case, our old and our new, and put them into a proportion. So if we look here, and we want to set up a statement of proportionality, we're going to start with our new on top. Our new, of course, is going to be UQ and ST, like so. But remember, if we have UQ, we must have it on the same side. And so for us, UQ on the same side is going to be this value of QR. And the same would be true for ST. If we have ST as a value here, we must use RS as the value here, just like so. Okay. Again, if we had it the other way around, if we had QR over UQ equals RS over ST, that's perfectly fine. Okay, you're going to keep the same consistency and you're going to find it to work every single time. But the key is consistency. Okay. And so from here, we can just solve. It'd be super simple for us. We're going to plug in all the values that we do know. So UQ we know is 9. QR we know, we just said it was X. ST we know is 6. And RS we know is 4. We'll cross multiply as appropriate. We get 36 equals 6x divided by 6 on both sides. We get x equals 6. And because we said x was equal to QR, by transitive property, we can conclude that QR equals 6. Now, this is what I like to call as the proportional way. The proportional way to solve it. However, I personally prefer the different approach, but something that we have seen in the past. And I don't really have a name for it, but I like to just say it's the old arrow new formula. Which, if you remember back from the previous semester, we know that old times k equals new. But I want us to be careful here. This is not k. Okay? This value, k here, is not the scale factor that we've seen in the past. Look at the two shapes that we shaded in earlier. Old is definitely a triangle. It's got 3 sides. But the new that we shaded in blue here is 4-sided. That is not a triangle by definition. Not a triangle. And in fact, it looks more like a trapezoid. Okay. And so because we know we're going from a triangle to a trapezoid, it doesn't make sense to say that's the scale factor. We change shapes. Okay. So we can't just change shapes and just say that this is the scale factor. It doesn't make sense. So we're going to adjust this equation here for our purposes. We're going to say old times p, the proportion, equals new. Now, what you may be asking yourself is, how do I find p? I don't know where to find p. And that's a valid question. However, we've already seen it before. And the way that we're going to see, I'm trying to find a different color. Let's try red. The way that we're going to see it is basically kind of how we did it in the past. If we found a segment that have 2 values, 2 numerical values in the previous part of the unit, we were able to find a scale factor like that. Well, that's the same approach we're doing here. We're going to take this ST over RS. We know that's new over old. And we know the values for it. ST we know is 6. RS we know is 4. Reduce it down. That's going to be equal to 1.5. Just like so. And so now we just plug in. We're going to take our old, which is QR, times our P, which is 1.5, equals our new, which is UQ, and we're going to solve. Well, QR is X times 1.5 equals UQ, which is 9. Divide by 1.5 on both sides, we get X equals 6. And would you look at that? We get the exact same answer both ways. Okay. I, again, personally prefer this one, because I think it's easier than seeing this whole monstrosity of a fraction. Okay. But do whichever way you prefer. But for the continuation of this lesson, I'm going to use the old to new formula. Okay. What I suggest is that if you are absent one day and you're looking at this video, I would take a pause on this, and I would try to do extra example 1 on your own. Okay. So that whenever you do need to find an answer, you can just continue with the video further on. But for right now, I would just pause the video, stop it. I would look back at this example whenever you need to. And so in this question, it's pretty much the same thing. We're going to take the exact same approach here, just how we did before. Because we know WZ is parallel to XY, this is proportional. We're looking for the length of VW. And this is what I was talking about earlier. Look, we already have an X in our formula, or not formula, sorry, in our diagram here. So don't reuse X. It's going to be confusing. Choose a different variable. Choose A, for example. Choose A, choose B, choose delta if you wanted to, but I don't know why anybody would use delta. It's kind of weird. But just choose a variable. Choose a different variable. And we're going to still follow our 3 steps. So old, new, proportion, and solve. Just like so. And just like how we did the other one, left to right, we'll just call it old, new. And so once I've set up my statement of proportionality, or if you want to just find your proportion, use just the 2 values that we know, and we'll figure it out. So we have new over old now. We're going to take, or sorry, first before we move on, I'm going to go ahead and label what we need to do. So we have old and we have new here. And I'm going to go ahead and shade those in. Shade in the other one. Just like so. And I'm going to finally establish what my proportion is. So I'm going to take the old of one side. Let's do the VX side of it. We'll take the old and put it on the bottom of our denominator. We have VW as our old and WX as our new. And that proportion is supposed to be equal to the other proportion. So we'll take the old of the second side, which is VZ, and put it in the denominator with a numerator of ZY, because that is the new of that side. And we'll just keep on going. We'll keep on trucking through. This is the point in time where you can use the proportion to solve it, or you can do the new old method or the old to new method formula. Either way, you're going to find your answer. But I'm going to take ZY and VZ, and I'm going to actually find the proportion. ZY is 8, VZ is 10. That gives me a value of 0.8. Or if you want to use fractions, 4/5. That works fine as well. Then I'm going to take my old times the proportion P equals the new as part of my formula. Replace the numbers in the values. So we have VW times 0.8 equals WX. Keep going. VW we said was A times 0.8 equals 12. Divide by 0.8 on both sides. We're going to get A equals 15. And that is our answer. But by technicality, let's go ahead and say VW equals 15. And that's that answer. Example 2. Here we have basically a word problem, but not quite as wordy as we may think. We have a word problem. We have a bunch of values written in right there. Okay, so we're going to go ahead and fill in our diagram. BA is 33 centimeters, 27 centimeters for CB. CD is 44 centimeters, and DE is 25 centimeters. Okay. Now, a word that a lot of us may not like is present here. Okay, the word explain. I find a lot of students do not like the word explain, because what that means, we got to write a sentence. and nobody likes writing in math. But we are trying to explain why the shelf is not, that's a good important word, parallel to the floor. Okay. But much like the previous two problems, we're going to set it up exactly the same. First step, always address old and new. Second step, find the proportion. Third step, solve. It's just going to be easier for us. So in this case, it's ambiguous as to what really is old and what's new. And so here's where we get to choose. Do we want BD, the segment BD right here, to be the old, or do we want it to be the new? Now, for a lot of my classes, we chose this one to be our old, but realize it doesn't matter which one you call old or new. Again, as long as you're staying consistent, you'll be just fine. And luckily here we have all four values. So we can actually put it equal to each other and see immediately and analyze what it's actually telling us. So let's make sure that we set it up correctly though. Always new over old. Setting up this proportion now. I like to start with the letters. If you do not like doing the letters first and you just go straight into the numbers, perfectly fine. Just make sure you're doing it correctly. I'm going to go with AB, BC equals BE over DC. Okay. Again, taking those same side segments, and we're using it for our example here. Because we know all these values, we can replace them. AB is 33, BC is 27, DE is 25, BC is 44. And now we look at this and we might think, yeah, we should just plug that into a calculator and see if they're equal to each other. But even before that, look at these fractions. Let's remind ourselves, what kind of fractions are these? The one on the left, this is what we call an improper fraction. The one on the right is what we call a proper fraction. Okay. And so if you remember from probably, I don't know, elementary school, improper fractions, those are greater than 1. But proper fractions are less than 1. We can't have a proportion that is both greater than and less than 1. That doesn't make sense. So because that doesn't make sense, this is not proportional. Okay, so that is our conclusion here. Not proportional. And so we reason it out. We're going to use that second theorem that we learned. Because it's not proportional, it is not parallel to the floor. But we have to put that into a sentence. Always, always, always into a sentence. So, since both sides are not proportional, this means the shelf and floor, that's okay, floor are not parallel. I think as far as a geometry answer, this probably should be fine. But I did add in by the converse of the triangle proportionality theorem at the end there. You can do it if you'd like to, but you don't have to. Again, just like extra example 1, I really suggest just stopping the video here in case you missed it the first time. Try it on your own first. If you get stuck, keep watching the video. But I'm going to try to speed run through this because our next class starts in about about 6 minutes, I think, something like that. So I'm going to try to speed run through this one. Here we have new values. What I would do is redraw the image. So a triangle like this, I believe we had A, B, C, D, and E. And so we're going to add in these values. So 35, 25, 20, and 28. Set up exactly how we did before. We're going to call the old BD and our new AE, and we're going to still set it up the exact same. New over old equals AV over CB equals DE over CD. Okay, again, we have all four values. We're going to put them all in place of these letters. So 35, 25 equals 28, 20. And then we're going to simplify. 35 and 5 have a greatest common multiple of 5. That reduces it down to 7 over 5. 28 and 20 have a greatest common multiple of 4, which makes this 7 over 5. And because this is 7 over 5 both ways, that means that we are proportional and that we are, in fact, parallel with the floor. Okay? And so for our sentence here, we would write, since the two sides are proportional, they are parallel. Oops, sorry, not they. I don't want to write they. We gotta be specific. Okay, be very specific. The shelf and floor are parallel. And again, I would just add in that by the converse to the triangle proportionality theorem. Just like so. Okay. And that's really it. I talked to Mr. Cruz, and this is about as far as we got. We skipped that third example here, but it really is quite a simple example here. It's just a little unconventional, but I think we'll be fine. I don't think this is even tested on the next two quizzes or something like that, so I think we'll be fine on this one. I don't think there's a huge need to go over this, but if there's some of us who do want to see it, you could definitely ask me or Mr. Cruz about how to solve it. But that'll conclude our first video lesson. If you are watching this and you have any, if you have any tips, tricks, or any commentary on it or any critiques, let us know, or rather let me know, because I'm going to be the one recording these. But yeah, just let me know and we will move on from there. Okay. Alrighty. Y'all have a great one. Bye-bye.